So as we get started, I'd like everyone to be aware of the EarthScope Code of Conduct. We expect that everyone at this meeting will be treating everyone with respect. You're going to be valuing the diversity of viewpoints and opinions. At all times, you will be considerate, inclusive, respectful, and collaborative where applicable. You will be kind to others. You'll avoid personal attacks, this be either verbally or in the chat. You're going to communicate openly, be mindful of your surroundings and your fellow participants. You'll always respect these rules, and communications at all time will be respectful and appropriate for a professional audience. So as EarthScope Consortium, we really are quite global. The NSF Engage and SAGE facilities that we operate are national. We would like to respectfully acknowledge the generation of peoples and communities that have been and continue to be the stewards of the land that we now use for our work. We ask that you join us in acknowledging their communities, their elders, both past and present, as well as future generations. This acknowledgement is one small part of our ongoing commitment to dismantling the legacies of settler colonialism. If you would like to see our notice stations that are on Indigenous territories, you can scan this QR code here. If you would like more information on historical territories of Indigenous nations, you can scan the other QR code. So as EarthScope Consortium, we operate 3 internship programs. The first is Geo-Launchpad. This one is targeting community college students. Specifically this year, we were looking at, and have been, community college students from Colorado, Wyoming, and New Mexico. These students participate in what we call like a pre-research or a research-ready internship program. They work with faculty at different institutions getting hands-on research skills. Our other internship program is RESESS, who you will hear from today, and I'll go a little bit more into on the next slide. And then our final internship program is EarthScope Student Career Internship Program. So these students don't do research, they work with EarthScope staff on projects where we need assistance with, so things that are vital to our different directorates. And they work internal to our organization. These are typically undergraduate and graduate students who are getting career skills that they can then apply to a career once they graduate. All of our programs are funded through the National Science Foundation. So RESESS, who you're going to hear from today, it is the program itself is a 1 to 2 year independent summer research internship program where students are focusing on earth sciences. This year, our goal was for us to have our programs projects to be primarily from geophysics. We aim for 75% geophysics projects because we are a geophysical facility. The goal of this program is to provide authentic research experiences and increase the diversity within the geosciences by providing a safe, inclusive, supportive environment for our students. I am the program lead. If you are familiar with the URISE program that we held last year, this is a combining of 2 programs that we had. So this year we had students that were based in one location as well as students that were satellite placed by themselves across the US. So highlights of our program, we focus a lot on career and scientific advancement skills. This starts with an orientation week where we get everyone together to get some hands-on time. We do field experiments, we do computer coding classes, lots of team building, some professional development. Throughout the summer, we work on scientific communicating and writing. So this focused a lot this year on developing poster presentations, which most undergraduate students will be assigned when they go to a conference. We have various levels of mentorship. We do field trips over orientation week and then throughout the summer at their various placements. And then ultimately, our interns will be attending a scientific conference. So the Geo-Launchpad interns that I referenced earlier will be going to GSA this year, and our RESESS interns will be presenting their work at AGU. We will be sending out emails to the community if you'd like to pop by their posters and see them. So our interns, this year we had 22 interns from 22 institutions. So wide range of types of institutions and locations and states were seen this year, which is great. That's what our goals are, to be broadly reaching. And again, funding, we are funded through the National Science Foundation in various capacities. Our RESESS and Geo-Launchpad interns are funded through GAGE, our facility grant. We also have an REU award that was awarded through the URISE program that we've absorbed into RESESS to fund some RESESS interns. And Geo-Launchpad also has a GeoPaths grant. additional support from all of our mentors and our graduate assistant and our staff. Truly, this work requires a lot more people than just a program lead. It requires an entire network and community to make it possible. So truly, thank you to all of you. I know our interns, thank you as well. Thank you for supporting them in person and virtually. And as I alluded to earlier, we did have several intern cohort locations this year. We had a cohort in New Mexico Tech, University of Colorado Boulder, Florida International University, University of Alaska Fairbanks, Sandia National Labs, University of Kansas, California Institute of Technology, and Penn State. Nope, that was last week's agenda. So our agenda for today is first, we will hear from James, and then Hassan, and then Serina, and then Jackie. So James, whenever you're ready, you can go ahead and share your slides.
Let me get that pulled up. 1 second. Slideshow. All right. Can y'all see that?
That looks beautiful.
Okay, cool. All right. Good morning, everyone, or good afternoon if you're on the East Coast. My name is James Genero, and I am a senior at Central Washington University. I spent the summer working with Dr. Catherine Materna at the University of Colorado in Boulder, and after 9 weeks, I'm very eager to share with you guys my summer research and investigation of coseismic and aseismic slip on the Imperial Fault, Southern California. Before I get into the details of my project, I wanted to cover some background information. The Imperial Fault is a right lateral strike slip fault located in the Imperial Valley of Southern California, which is south of the Salton Sea. While this fault is primarily strike slip, there is normal faulting observed in the northern segments that bounds the Mesquite Basin. In 1940 and again in 1979, this fault produced large earthquakes, magnitude 6.9 and 6.5 respectively. While this fault moves in large ruptures, it's also been observed to move in creep events. Creep events are defined by their slow movement of a fault, usually over days or weeks, and does not produce an earthquake. The Imperial Fault has had at least 8 distinct creep events since 2015, and we're confident there's been more. Oops, wrong slide. How'd I go? There we go. There were 3 main objectives for this project. 1, digitize the slip distribution models of the 1979 Imperial Valley earthquake. 2, determine the parameters of each observed creep event. And I'll explain what I mean by parameters on the next slide. And 3, understand the relationship of these creep events in relation to large historic ruptures of the Imperial Fault, such as the 1979 Imperial Valley earthquake. This project used a variety of tools to accomplish the objectives. For digitizing slip distribution models, we utilized published literature from Archuleta, Sharp, and others. We identified creep events using GPS time series, creep meter time series, and INSAR. We then recreated the observed dislocations with hypothetical dislocation modeling. For the analysis, we plotted the creep events with the slip models created from Objective 1. Moving into results, Objective 1's results is represented by the figure on the top left of the slide. The dots above the plot represent surface offset from Sharp and others. The brown to blue color scale seen on the top right of the figure represents dip-slip offset. Note, this scale is on the order of centimeters. We see that the dip-slip offset is limited to the northern end of the 1979 fault rupture. The other color scale is strike-slip offset. This scale is on the order of meters. You can see that the maximum slip occurred at depth about 10 kilometers down the plunge of the fault. Moving on to Objective 2, these results are represented by the table on the right. The parameters we explored are in the highlighted columns or columns 4, 5, and 6. The rupture length, or L, is the length of the creep event along the fault, essentially the rupture length. The amount of slip is how much the fault moved. The top depth, or Z, is how close to the surface this creep event got. The width, or W, is a proxy for depth. The highlighted rows represent dip-slip creep events. The others are strike-slip creep events. These variables are shown in the figure above the table. In general, we discovered that these creep events are small events, slipping on the order of tens of millimeters and rupturing on the order of a few kilometers. These events are very shallow, and most events come close to rupturing to the surface. However, we are now starting to think that more events rupture to the surface than not. With these tiny events, they are equivalent to tiny magnitudes, no smaller than magnitude 3.22 and no larger than 3.85. For objective 3, represented by the table on the bottom left, you can see that the creep events are occurring um, in relation to the 1979 rupture. The creep events are shown by the elongated rectangles. Please also note the difference in slip scales, with the creep events scale ranging from 0 to 40 centimeters, and then the 1979 rupture ranging from 0 meters to 1.6 meters. Essentially, these creep events are occurring at shallow depths, entirely confined in the sediment layer. Because of this, we can infer that the imperial fault is weak and cannot hold much stress towards the surface, and that the fault is stronger and/or locked at depth. We observed creep events occurring north of the border of the US-Mexico border, but we believe they are occurring all along the fault. In the figure on the top right, we can see that the amount of slip from creep events is not scaled by how long the rupture length. However, on the bottom figure, we can infer that the deeper creep events actually produce more slip. Because of the ratio of slip to depth in these events, we can actually estimate an average stress drop of 24 kPa per event, which is really tiny. With that stress drop and inferred stress accumulation rates of the region, this indicates any given area of the imperial fault would experience a creep event every 3.5 years. The main motivator behind this work is because the movement of faults can transfer stress along the fault or even to nearby faults, and in some cases can trigger other events. It's also important to understand the behavior of stress transfer for this fault while it's in the interseismic, or dare I say, the late interseismic period of the earthquake cycle. To build upon this research, we could use more instruments to locate and model all measurable creep events. We could explore the stress relationships of this fault with nearby faults, or we can explore making slight changes to our methodology to assess the accuracy of our data. I would like to thank the National Science Foundation for funding this research, and I will be happy to answer any questions. Thank you.
That's great, James. So if you have any questions, you can raise your hand or you can put them in the chat. Okay, question from Moira. She says, great presentation, James. I was wondering, how did this project align with your passion for geosciences?
Yeah, great question, Moira. Well, before this summer, I had two big interests in geoscience, volcanoes, and tectonics. And so I was very excited to be able to work on this project because I finally got to explore more of my tectonic side of my interest in geology. It helped me realize that this stuff is really interesting and that there's just so much going on that even a 9 to 10 week project is not enough to even start scratching the surface. Any other questions?
I have, I have a question. It's related. You kind of led into it. Um, how how has this influenced or shaped what you're looking to do next? If you're looking to do more research, because you kind of alluded to like 9 to 11 weeks, that's not that long.
Um, yeah, like in terms of this project,
That or just
um,
your general research interests for the future. Like, are you looking at internship programs? Are you looking at graduate school?
oh yeah, well, my next steps is looking at graduate school. But I think volcanology still has like a tight grasp on me. However, I am interested in utilizing the sort of the same methodology for other like volcano related research. Because while our methods was kind of tough for me, um, I think it's really valuable, and I'd be interested to learn how I could utilize it for other areas of geoscience.
We have a few questions in the chat. Christine would like to know, do you have any GNSS plots showing the creep events?
Not on here. However, I do have a folder of a lot of stuff. If you wanted to reach out to me, I can share with you some of those plots and figures that I have from when I was modeling these events.
Another question from Ellis. Awesome work. One, were you able to constrain the duration of any of the creep events? And two, did you look into potentially triggering relationships due to the regional earthquakes?
Yeah, I'll answer the first question. Concerning the duration was kind of a challenge with our interferogram since they're in a 12-day period. Um, so we could see like in a creep event in one interferogram, because that's a 12-day period, but we couldn't really get uh more than that. However, I guess we do have the GPS and the creep meter time series. Um, However, with how long they exactly last, it was kind of hard to tell, since the interferograms are in 12-day periods. And then the second part of your question, um, we didn't look into that. Um, we didn't look into that particular aspect. I know in 2010, a creep event was triggered from an earthquake south of the U.S.-Mexico border. But we didn't really explore like triggered creep events from the ones that I modeled.
One more question from Christine, which says, sorry, it just moved. Um, the area between the Salton Sea and the Gulf of California is prone to seismic swarms. I seem to recall at least one swarm near the border, maybe. Are the swarms something you would consider in hypothetical future work?
Um, let's see. I can't give a hard answer. But because there's just so much going on there. So I guess it would be interesting for distress relationships with how those swarms affect stress of like the imperial fault. It's something I wanted to explore, but I didn't have enough time, unfortunately.
Fair. Okay. Thank you, James. If
Thank
anyone
you.
has any follow-up questions, you can put them in the chat and he can respond to you there. Okay, up next, we have Hassan.
Did you all see my screen?
Yes.
All right. Hello everyone. My name is Hassan Saleh, and I have had the pleasure of working with my two mentors, Tushar Mittal and Krista Wathier. And I attend the University of California, San Diego, and I'm currently doing research at the Pennsylvania State University. So the title of my project is exploring the role of geophysical processes on mid-ocean ridge depth, a data-driven analysis. So first and foremost, the scientific question that I will be diving deep into today is what controls the variance in mid-ocean ridge depth globally. And figure one is a figure of the world map of mid-ocean ridge locations with the corresponding depths. And some background is that mid-ocean ridges are composed of 60,000 kilometers of long chains, and they vary in depth by approximately 8 kilometers. They range from negative 6.5 kilometers to roughly 2 kilometers. And below mid-ocean ridges are deep, usually greater than 250-kilometer depth mantle material that is fed to the ridges by passive convective currents. And these currents result in decompression melting at shallow depths of usually less than 150 kilometers. And this is how new oceanic lithosphere plates are formed. And figure two is a figure of the variation of mid-ocean ridge depths across oceanic crustal age. So the way in which we would test the two N members is by using mantle temperature structure. And this is estimated using seismic tomography um, models such as the one in figure 3. And we use these values to convert them into temperature as shown in figure 4. Also, we will be looking at hotspot locations as shown in figure 3 in the pink circle, and their distances from the plume and what their effect is on the depth of the ridge. So with this data for all mid-ocean ridge segments, we will be able to use a machine learning tool named Orange, and embedded in the model are linear regression as well as nonlinear models, such as KNN, random forest, and ADA boost, highlighted in pink. And also, we will be using feature importance and explain models in purple to determine the most relevant parameters that the models used, as shown in purple. So after trying out several unique data sets, the one that gave us the best model was composed of principal components 1 through 5, which is based on mantle temperature from 100 to 600 kilometers in 20-kilometer increments. Also, we had the max temperature at 100 to 600 kilometers within a 500-kilometer radius of the ridge, and we also included hotspot features. And after we ran the models, the regression values told us that the best model was the random forest model. And here in figure 7, we have a scatter plot, which shows us the model prediction values on the y-axis when comparing it to the actual mean depth values on the x-axis. So to look at which features gave us the greatest contribution, we have in figure 8 the feature importance with the greatest contribution on the top and the least on the bottom. And we see that the greatest contributions came from partial temperatures from 100 to 180 kilometers, and also hotspot features. And these feature contributions were PC 1 through 5, and they did not make the top 10 features. Figure 9 on the right is a map of the uncertainty of the model predicted depths, and the clearer, like whitish circles, have a less uncertainty, and the darker ones correspond to a higher uncertainty. So in conclusion, we find that shallow melting processes and hotspot features are key controls on the ridge depth, with secondary roles of large-scale mantle flow. And there's ongoing work of analysis for other ridge properties, such as spreading rate, and assessing the role of ridge geochemistry to understand the role of shallow melting. And finally, I want to thank the National Science Foundations for their grant and for helping me with this research project. Thank you. And I'll be happy to answer any questions.
Great. The floor is now open for questions. Okay. I can start what everybody else thinks about it. So Hassan, you're a returning intern, right? And you're also on the quarter system, which allowed you to have like a little bit more flexible time in starting. What made you choose this project, and what are you hoping to get out of it? Because you still have some work before you're done, like in terms of personal growth, I say.
Yeah, we're planning. So I presented this project on looking at the mean depth. We're also going to look at the spreading rate and the the geochemistry. So that's the plan moving forward. Last year I worked on like volcanic ash samples, and it's interesting to kind of see the broad spectrum of geoscience and actually work on like the geophysical work of rich segments.
Thanks. We have a question in the chat. Moira says, awesome job. What was the most challenging part of this internship for you?
So far, the most challenging work would be running the data set on Orange. It's just time consuming, but other than that, it's been going well with the help of my mentors. So yeah.
Great. Shelley says, fantastic work. How are you collecting the geochemistry data?
So the geochemistry has been collected. They're in a file. So the similar thing was worked on with partial temperatures. So we use file collected by previous researchers. And so I use the geochemistry from the data and I run it through Orange. So I would just have to run it in order to look at the results and interpret them, essentially.
Okay. I think that's all the questions. Okay, thanks, Hassan. This was great.
Thank you.
If anyone thinks of more questions, you can put them in the chat and he'll answer them there. Up next, we have Serina. Whenever you're ready, you can share your screen.
Sounds good. Looks all good.
Beautiful.
All right. So hello everyone, my name is Serina Wang and I am a EarthScope RESESS summer intern. Over the past 10 weeks, I've been looking at data that is seismic, infrasound, and converted local infrasound, trying to see how well does converted local infrasound act as a proxy of seismic arrivals. But also, we have approached a seismoacoustic method in uncertainty reduction when it comes to calculating explosion yield and height of burst, seeing how that can help reduce errors and uncertainty. So before I get into the actual project, I wanted to prep everyone on what is the difference between seismic and acoustic data. Essentially, seismic data is what traditionally has been used by geophysicists and seismologists when they study earthquakes, volcanoes, explosions, and whatnot. And these are body and surface waves that travel through the solid earth. On the other hand, acoustic waves are sound waves traveling at a frequency of below 20 hertz that also help scientists study very similar natural and man-made phenomena. However, they travel through the Earth's atmosphere instead of the solid Earth. And on the right here, we have a station map of all the stations relative to the ground truth of the DAG4 data, which is the explosion that we will be looking at today. In green, we have the infrasound stations, and in blue, we have the seismic stations. And wherever you see two stations overlapping each other, we will be referencing to them as the co-located stations. So now that we know what is the difference between seismic and acoustic data, we can then talk about the converted local infrasound data. So essentially, on an infrasound data recording, there's a possibility for seismic events or seismic signatures to be picked up by these infrasound stations and therefore reflect in the infrasound recordings. And by using the McPherson et al. Method, we can then convert these infrasound data into converted local infrasound data, which then can act as a seismic proxy for seismic arrivals. And I like to point out here, over the first onset peak, we can see the orange dashed lines that are the converted local infrasound data matches up relatively well with the solid blue line that is the seismic data. And with these data, we can then use the Ford empirical model and plot these likelihood plots that is shown on the right here. And figures A and B are the seismic likelihood plots, while C and D are the converted local infrasound likelihood plots. You can see when compared side by side, the likelihood plots show a very similar shape. However, just that the converted local infrasound has shifted the likelihood plots to the right a little bit, indicating it is estimating a higher yield than the seismic. So now that we have all three kinds of data, seismic, infrasound, and converted local infrasound, we can then talk about the uncertainty reduction aspect of the project. Research has shown when seismic data and infrasound data are used separately while calculating explosion yields and height of burst, a trade-off between the accuracy of those two values are observed. In order to mitigate that trade-off, a seismoacoustic approach is then needed. So for our project, we have implemented a seismoacoustic approach through multiplying the seismic likelihood matrix with the infrasound likelihood matrix. And the result is shown here on the right, where you can see the maximum likelihood yield area is constrained and the trade-off is mitigated. Over here, you can see the gray dot represents the actual known ground truth of the yield and height of burst plotted, while the black star represents where the maximum likelihood value of the yield and height of burst locates at when we multiply the two matrices. And I'd like to point out here, we can use the converted local infrasound as we discussed before in place of the seismic data and do the same workflow and calculate the likelihood that way. So to summarize the project with some take-home messages, we can say that the converted local infrasound does appear to work well as a proxy for seismic arrivals. However, small differences in the displacement or duration of the first onset peak could lead to large differences in the estimated yield. And that is shown in numbers here. We can see that the converted local infrasound does a good job estimating the height of burst, but not so much when it comes to the yield, while the seismic does a relatively good job for estimating both the height of burst and the yield. We think that the converted local infrasound is overestimating the yield by such a large percentage because of possible wind noise that may have been picked up by the local infrasound stations, and thus resulting in higher amplitudes of these infrasound recordings and larger displacements, causing larger yields. And I'd like to thank the NSF for funding the project, but also Sandia and EarthScope for helping me throughout the project. And I can take any questions now.
Great job. Floor is now open for questions. Yes, Shelley.
Hi, Serina. Great talk there. Very interesting to hear about both the seismic and infrasound. And so I have a question. How are the speeds different? You know, for the first arrivals, it looks like they align really well, but is that after some processing? And then you mentioned that you were using an explosion as your source. And so I was wondering, how are these data used in real life?
So over here on this plot, we can see the first peak matches up really well because these are infrasound recordings where it picked up the seismic event arrival, while you can see around here where the green dash line is, this represents where the actual primary infrasound arrives in the infrasound data. Does that make sense?
Yeah, so it sounds like the later signals are shifted.
For the infrasound, yes.
For infrasound, yeah. And then real world, is this for nuclear testing treaty?
I'm not sure how much I can say, but yes, explosions and this method can also be applied to volcanic explosions and mitigating those hazards, I believe.
Good answer. Thank you.
Of course, thank you.
All right, we have some questions in the chat. Moira, she says, amazing job, Serina. I loved your figures. What was the most rewarding thing that you've accomplished over the summer?
Thank you, Moira. I would say just watching my code run and that it works. That's probably the most rewarding part. Because research, yeah, everyone knows research, you go do it, but then you run into problems like the data doesn't work or it's not neat enough or the code doesn't work. It's all frustrating, but once it starts working, it's really rewarding.
I think that's a common thread that I've heard from you all this summer. It's like, my code doesn't work. Oh, it works. Hooray.
Yep.
Fair. Christina has questions. She says, what is DAG4? If wind noise can distort results, is there some preferred topography for using infrasound? For example, mountains versus plains.
So DAG4 is short for dry alluvium geology, and it's a series of explosions for testing by, I think, Sandia. Not super sure, but DAG4 just means we're using the fourth explosion of that series. And there are ways to help reduce wind noise in infrasound data, such as shielding the infrasound stations with a bush or like a cover. And there's also ways to filter the waveform, I believe, by such as looking at the signal to noise ratio and filtering out the trend of the amplitudes that comes before the actual signal arrival. Is that all the questions from that? Okay.
Yeah, you covered it. Okay. I think that's it. Thanks, Serena. If there's any follow-up questions that you all think of as you're sitting here, feel free to put them in the chat.
Thank you.
Okay. Last but certainly not least, we have Jackie. Whenever you're ready, you can go ahead and share your screen.
Can you guys see this?
Yes, it looks great.
Okay, perfect. Hi guys. My name is Jacqueline Silva, and I was a virtual intern working at Boulder University. And my project is time frequency analysis of GPS displacements for monitoring changes in aquifers and geothermal fields in California. And I worked with Jose Lopez and Julie Jiang. So, our objective is to use GPS time continuous data to observe changes in tectonic movements in relation to faults, geothermal energy extraction, fluid injection, aseismic movement, and local earthquakes, as well as to view subsurface displacement of stations on top of an aquifer system in relation to seasonal changes as well as groundwater pumping in the area. And for the purpose of this presentation, we're going to be looking at two stations. And the first one is located in Brawley, the Brawley seismic zone, and it is pinned at the bottom. Our second map is just a zoomed in version. And the red lines are showing a historic fault, which is a fault that has moved in the past 200 years. And as you can see, our station is located right on top of that. And the last map is showing our very next station, which is CRCN, located in the Central Valley Aquifer. This map is showing the total displacement from 2015 through 2024. And as you can see, our station is located in one of the highest areas of subsidence. Okay, for creating our plots, first we went to the Nevada Geodetic Lab and Scripps Orbit and Permanent Array Center, and we picked out areas of interest. Then we utilized Google Colab, where we created a line of code, which made it that Python can read both of those databases. Next, we exercised the modules matplotlib and numpy, which helped process, filter our data, created the plots, and that presented GPS movement in relation to time and speed. And lastly, we looked at the plots produced and modified it into a final product. So these are our time frequency analysis plots. And at the top, you can see the time series plot, and at the bottom is the time frequency. And they all have three directions, north, east, and z, which is up and down. And for our first station in the Brawley geothermal field, we're going to be looking at the top left plot. Here we see a large shift north in 2012, and this was due to a tension release of a strike slip fault causing a magnitude 5.4 earthquake, and the station was 5 miles away from the epicenter. After this earthquake occurred, there was a swarm of earthquakes that followed called the Brawley Swarm. And next we're going to be looking at the time frequency plot underneath that. And as we can see, there's some yellow, green, and dark spots. And these colors are showing the different intensities of the frequencies. The first bright yellow peak shows an occurrence with the 2012 earthquake and shows intense frequency. And from 2012 through 2016, you see like a gradual decrease in intensity, or it's turning more green. And this is due to a decrease in geothermal activities as well as the ending of the Brawley swarm. And as for the dark areas, this shows as no frequency due to data gaps caused by equipment changes at the GPS station, sorry. And then for our second station, we're mainly focusing on the time frequency at the bottom. We see some recurring patterns of bright yellow with spaces of green in between it. And this is in congruence with the seasonal changes in the aquifer. Importance and future work. Importance, observing tectonic movement is important to help mitigate hazards that might come with geothermal extraction and fluid injection by looking at that area's seismic past. And time frequency can provide a visual representation of ground movement that can be helpful for observing aftershock and seasonal changes. For future work, we're going to choose more stations in the Central Valley Aquifer to compare data, as well as collect more data on the 2012 Brawley earthquake in relation to a swarm of earthquakes that occurred in the area. And personally, I would like to expand my knowledge on the hazard of fluid injection and geothermal energy extraction, so close to a fault line. I would like to thank the NSF and EarthScope. And that's it.
Great. Thanks, Jackie. Okay, the floor is now open for questions. Okay, Catherine has a question. She says, did you try this analysis on any other GNSS stations near Brawley yet? Any similar signals?
I have not for Brawley, but I do know that that's an interesting topic for Catherine because I did read her paper, and I will be looking further into that for our poster.
Okay. Laura says, Jackie, such a wonderful presentation. I know remote work comes with its own challenges. How did you manage those?
I think I was able to manage being remote due to the people that were with me in Boulder, like Juan, James, Louisa especially. Whenever I had issues with creating my plots, I always went to James and Louisa, and they helped me because they had some coding background. And I believe that was very helpful, as well as creating a schedule for myself and holding myself accountable.
Yeah,
Thank you for the question, Mara.
it's a great question. Shelley says, great presentation and combinations of data. How is this, if it is, guiding your future course selection and future research?
So for future research, I would like to explore geophysics a little more, because before this internship, I was more leaning towards geochemistry. But I like learning, and this was fun, and it was an interesting project. So I would like to look more into this topic.
Okay. Any other questions for Jackie? These have all been great questions. No, I think that's it. Great job, Jackie. Okay, that brings us to the end of our presentations for today. I want to thank everyone for joining us. Really appreciate all of your support of our programming. We could not do it without you all. If you're wondering, what are the interns going to do next? They're all going to AGU, and I will send out a list of their presentations. If you have any questions about internships, you can email internships@earthscope.org and we will get back to you. Thanks for joining us.